In this video, we will discuss the curl of vector fields. Curl of vector fields has significance in fields that describe swirling motion, usually produced by vortices. So let me read the curl of a vector field A. So a curl of a vector field A at any particular point is actually a vector, um, an actual vector. And being a vector, it has a magnitude and a direction. So the magnitude is stated here as the maximum circulation of vector A per unit area as that area tends to go to zero. And the direction is the normal direction of the area when the area is oriented to make the circulation maximum. Let us discuss this in more detail by going to the formal definition of the curl of a vector field. Here is the mathematical definition of the curl of a vector field A. So to explain, let's imagine that we have a vector field here, vector field A represented by the green arrows. And let's say in that vector field, we define a small area bounded by the curve L. So this area is shown here as delta S, and it is enclosed by the curve L. Let's say we have a point L sub 1, and let's examine the vector there of the vector field A. So let's say that vector there is A sub 1, and let's define another vector dl, which is directed along the curve L as shown. And let's say I'm going to take the dot product A1 dot dl. So this dot product will give me a scalar quantity that or is the scalar quantity or the contribution of the vector A sub 1 along the path dl, which is uh, along the curve L. So that contribution by the vector A sub 1 is actually there along the path and tends to rotate the area in the counterclockwise direction. Let me pick another point L2 here. So there's another vector there, A sub 2. Again, let me do a dot product, A2 dot dl. So this dot product will yield the component of A sub 2 along the path of dl, which is along the curve L, and will also make a contribution uh, along that path. But since the direction of A sub 2, the component along the L is of the opposite direction to the L, that is the dot product, the contribution of A sub 2 on the area tends to rotate the area in the clockwise direction, which is in contrast with the tendency contributed by the vector A sub 1. So we do this along the curve L. So we sum up all the contributions of the vectors along the curve L, and that sum is actually caught by this contour integral. Okay. In addition to that, let us uh, assume that we can orient the area in such a way that it will give us the maximum contribution of the sum of the contributions of all the vectors along the curve L, whether it may be clockwise direction or in the counterclockwise direction. After summing up and orienting the area, we then divide the result by the area itself, and we would get some result. Then we let this area shrink until it becomes an infinitesimal area, and then get the limit if there is a limit uh, when the area becomes very small. Let's assume that um, the limit has a value. Also, we recognize that a, uh, a unit vector a sub n max can be drawn that is normal to the area and whose direction is or follows the right hand rule. So if the tendency of the area is to rotate in the counterclockwise direction, that direction of the unit vector a sub n will be in this direction. But if the area tends to rotate in the clockwise direction, that direction of a sub n will be in the opposite direction as shown. Then we put together the limit that we have uh, got earlier and associate that with the unit vector a sub n max. And then what we get is actually the curl of the vector field A at point P. Okay, so that is the explanation of this mathematical definition of the curl of the vector A at point P. To add on the previous slide, so the curl is nicely defined by the del operator crossed with the vector field A. So we assume the del operator to be a vector, and we do a del cross A, and that gives us the curl of the vector field. Here is another illustration of the curl at point P. So let's say we have here a field that is shown as a circulating field. So the curl at point P can be regarded as the measure of circulation at that point. Also, in the right side, since, or we can say that the curl is zero there, because obviously the field is running in parallel lines at point P. Here is an actual picture of the magnetic field intensity inside a single thick wire. So shown on the left side, we can say that at any point in this drawing, we can get a curl. Also, on the right side, this is the magnetic field intensity of a single wire. on the outside of the wire. So again, we can say that there is a curl at any point in space here. So here are some statements regarding the curl of a vector field. So the curl of a vector A is the measure of the strength of the vortex source of vector A. Uh, Usually the curl is due to a vortex source. So if we can measure the curl at any point in the vector field, that is an indication of the strength of the vortex source that produced the curl in the first place. The vortex source is a source that causes a circulation of the vector field around it. Uh, so this is a follow-up statement on the first statement that the circulation of a vector field is caused by a vortex source. So the third statement says that the vector field whose curl is zero is an arotational vector, meaning the vector field, the way you see it, there's no rotation that is going on. Okay, so we have defined earlier that the curl of a vector field is defined as this one. So it's del cross A if we're talking about the vector field A, and that is given by this in Cartesian coordinates. If we are dealing with cylindrical coordinates, this will be the expression, and for spherical coordinates, we can use this expression. So take note that the curl of a vector field produces another vector, and there is no such thing as the curl of a scalar field because the curl always refers to a vector. So here are some identities pertaining to curl of a vector field. So here this is the curl of the sum of the vector field. So it is actually equal to the sum of their curls. Okay, so the sum of the curl of A and the curl of B. Now, if we have a vector field multiplied by a scalar, the curl of that is defined as the curl of, as first we multiply the del by k, then we do a k del cross A plus the gradient of k cross A. Another identity is this one. So this is actually the divergence of the curl of A is actually a zero. And the last part is the curl of the gradient of V is also a zero. So let's have some examples pertaining to curls. So let's say we have here vector fields. One is in Cartesian, the other one is in cylindrical. So we are required to determine the curl of these vector fields, and we evaluate those vector fields at these points. Here is the solution. So the P here is expressed as a Cartesian or in a Cartesian coordinate system. So we use this formula. Um, so um, so we then expand this determinant. So for the x component, we multiply this. So here it is, less this one. So it is here. Then we multiply this. So this is it. And then the other one is this one. So here it is. And lastly, we multiply this one. So and less it by this one. Okay. Then we evaluate. So here, this is 1. And here is we are taking the partial derivative with respect to z of this one. So we have this a constant. So this becomes a 0. Here we take the partial derivative with respect to z of yz. So here we will get a y. Here with respect to x. So therefore this is also a 0. So that gives us the y component. So this is the x component. Here we do a partial derivative with respect to x. So that should give us 4y. And here this should give us z. So it is shown here. So therefore this is the curl uh, of the vector field P. And at this point, we simply substitute the coordinates to the curl, and that this is here, and we should get this vector here. So this is the curl of the vector field P at the points coordinates 1, -2, and 3. For the second question, so the field is written as in cylindrical coordinates. So we use the formula for cylindrical coordinates, which is this one. And so expanding this one, that will actually give us this one, which will give us a field that is this one. Okay, so this is the curl of the field Q that gives us a vector field as well. And substituting the coordinates in a cylindrical coordinate system, so that should give us this vector. So this is the curl of the vector Q at point this point. So it is given by this vector. So that wraps up our discussion on vector calculus, and on our next series of videos we will be talking about static electric and magnetic fields, and apply our knowledge, what we have learned so far about vectors and vector fields.